Hello, welcome everyone. Welcome to our today's webinar. It's about teaching LQR, LQG with accessible MIMO experiment systems. And we will be going through the presentation and a short demo in today's presentation. Welcome, Dr. Fethi Candan, and also welcome to Dr. Ahmet Arıca. Thank you for joining me to today's call. And we will be spending like 30-40 minutes of time together, and we will be showing some very nice presentation and demonstration today. So, okay, let's start with our presentation. Yep. So today's topic, and first of all, I would like to introduce our guest speakers, Dr. Fethi Candan and Dr. Çağrı Arıcan. So let me start with Dr. Fethi Candan. He is an assistant professor in the Department of AI and Data Engineering at Ankara University. Dr. Candan holds a double bachelor's degree from Bilecik University with a Bachelor's of Science in Mechanical Engineering and Bachelor's of Honors in Electrical and Electronics Engineering. He then obtained his Master of Science in Control and Automation Engineering from Istanbul Technical University. This is where our company is started as well. And following that, he did his PhD in Automatic Control and Systems Engineering in the University of Sheffield in UK, United Kingdom. So bringing a strong international background to his work, Dr. Candan gained extensive teaching and research experience at institutions like Sheffield Hallam University in the UK and completed his postdoc in mechanical and dynamical systems at the University of Idaho in the United States. His current research focuses on robotics, artificial intelligence, control systems, and human-computer interaction. We are honored to have him with us today. It's also my pleasure to introduce lecturer Dr. Ahmet Çağrı Arıcan. He is a research assistant doctor in the Department of Mechanical Engineering at Gazi University. Dr. Arıcan is a dedicated alumnus of Gazi University, where he completed his academic journey, earning his bachelor's, master's, and recently his PhD in this department. His extensive research specializes in nonlinear control systems, system dynamics, robotics, mechatronics, and the modeling and simulation of dynamic systems, such as the MIMO experiment kit that we will be discussing today. Dr. Arıcan contributed significantly to international conferences with his work on advanced control theories. Okay, thank you again, Dr. Çağrı Arıcan and Dr. Fethi Candan for joining us today.
Welcome.
We will cover today roughly 10 topics or sections. This is like around 20 slides, as well as like a live demo session. I will be going through some of the slides, but Dr. Candan and also Dr. Arıca will be assisting me or taking step whenever their parts or the parts they know better than I. So having said that, let us discuss about the topic of today's presentation. So what is a multivariable control system, MIMO control system, and how is it different from a single input, single output system? So first of all, the abbreviations SISO and MIMO. So they represent single input, single output as SISO, and multiple input and multiple outputs abbreviated as MIMO. The figure on the bottom can help me to explain the differences. So a SISO system, as the name stands, there is a single input that you give to a system, which is in this case a conveyor belt. So we control the speed or maybe the position of the electrical motor, and that electrical motor rotates the conveyor belt, and any object on the conveyor belt moves according to our direct input. And there is a kind of one-to-one relation although there is a kind of a coefficient, so maybe we need to rotate the motor multiple turns or times to make the conveyor belt move a couple of centimeters or meters. It really depends on this input shaft section, but this is just like a linear coefficient in that sense. For as a MIMO system, which we just put a robotic arm here, that is another like very well-known MIMO control system. There are always multiple inputs. Like in this case, like a 6DOF robotic arm has 6 electrical motors, and each input has some effect on the total output of the system. So, for example, if we apply some input to the motor number 3, which is U3, the end effector, the gripper that is seen over here at the end of the robot, it will move, but it will move in very different directions as well, not only a single direction, but in multiple domains or multiple directions. So that makes the control of this output, this point, or end effector point, a little bit more difficult compared to a single input and single output system. So this is one explanation of the MIMO setup, but better explanation will be towards our today's experiment system, which is like a twin rotor helicopter or its own model that we call 3DOF helicopter. So Dr. Fethi, can you please help me explain these like axes and how they are related to each other?
Thank you so much the previous explanation about us and the presentation as well. Now we can talk about what is that in the twin rotor systems in the real world actually. And anybody knows about the different type of the helicopter models actually. Generally, we know that one of the bigger propellers and the small propellers. But the constraint there, especially for the cargo types helicopter, they have 2 big propeller systems, such as Chinook 47, this one. And the constraint for the attitudes, they have 3 different type of attitudes. The one of them is the travel axis, that means the here, and another one is the elevation axis, and the other one is the pitch axis. Pitch axis gives to us the 2 propellers and the effects. So that means the constant elevation is the main rotor thrust. So that means this part, and the traveler also gives the tail rotor thrust, and the coupling gives to us the speed changing in the rotor. So that means we have 2 rotors, and we can see the coupling effects directly inside the helicopter model. And we can do the second. Yeah. Okay. So that means how can we model and how can we determine the mathematical model, block diagram, and the engineering parts. So here it is. We have on the travel axis, on the pitch axis, and the elevation axis. So we can determine the each blocks, and we can understand where is the coupled dynamics here. And if you consider the classical pitch dynamics, they have only the one input. The output gives to us the pitch values, pitch attitudes, and the pitch angular velocities. But the constraint, the travel and the elevation dynamics, they are directly the input and output between each others. So that means gives to us the coupled dynamics inside the block diagram. Okay, and in the next slides, and consider the engineering lectures, in the classical lectures, we learn about the general state space representation. That means considering the standard form, we have x dot equals to ax plus bu and y equals to cx plus du. So what does that mean? These a, b, c, d, x, and y. So x gives to us the state vector. So that means elevation, travel, pitch, and their angular velocities inside the states. And u gives to us the input vectors. So that means we have 2 rotors. That means the rotor vectors for us, rotor's thrust for us. And the y is an output. So that means pitch, elevation, and the travel. And if we use the derivatives, and we can access also the data angles as well. And so that means we have A, B, C, D, and that means the material and the matrices for the systems dynamics. A gives to us the state matrix, B in input matrices, C is sensor matrices, and D is also disturbance matrices as well. And we can determine the classical block diagram in the right side as well.
Okay, perfect. So this gives the baseline of the like maybe the experiment itself, but
Yeah.
we also maybe need to define the like our goals or and how it is like related to the performance of the control. So for that, I think maybe Dr. Arija can help us introducing the cost function maybe first, and also the gain matrix of the state space represented LQR.
Yeah, thank you very much.
Yeah.
And
Raja,
this
so
system,
your voice is on mute probably on StreamYard. Can you unmute? So
okay. No,
maybe somehow. Okay. Now it looks like. Okay, so please go ahead. That's my bad. We can hear you
is there any
now.
problem?
Please go ahead.
Is there any problem?
Are you sure? Oh, we are hearing, he said. Oh, it's okay.
Okay, thank you. And thank you very much. And this system is a under-actuated system, and it has 3-axis motion, and there are 2 motors, and therefore we regulate the 3-axis, but we track the system in 2-axis. Therefore, if you want any LQR or optimal control, you must be careful to design the controller. In LQR controller, there is a cost function, and you want to minimize this cost function, cost function, and this system input multiply with gain matrix and state vector, and we give the system, we apply the system this U input matrix, and cost function is we want to minimize this cost equation, and Q and R is controller parameter, R is input parameter, and Q is state parameter. If you change the Q matrix, and if you increase the Q matrix, you obtain better transient response of the state. But if you increase the R matrix, you apply the system less input, and you design the Q and R matrix for obtain desired transient response and desired input bound. And gain matrix from the algebraic Riccati equation. P is the solution of the algebraic Riccati equation, and you can use the MATLAB function, LQR MATLAB function, and Y better for MIMO system. K is a full state matrix, and every input responds to every state, and this couple system. And if you want for example, you desire to track the travel axis, you it's all you also control the pitch axis, for example, and you track the 2 axis, but the other 1 axis is regulate. And
so that means it's the equicoordinate y better for MIMO. We have to first determine the full state matrix system. We can understand the cross coupling, am I right, on the A matrices. So that means it's easy way to determine how can we find the gain, the key gain values with using the Riccati solver, Riccati equation and Riccati solver.
Yes. Okay. So now Then
And
there is this software implementation.
there
Chart.
are system parameter and system metrics, and we can select the A and B metrics for design the LQR controller, and C is the output metrics, and in here we control the elevation and pitch axis, and we select the elevation and pitch axis row, and D is the disturbance matrix, and there are normally there are four state in this system. Now we give the four row and four column metrics, and there are two input, and we want to control the two axes normally, pitch yaw and their angular velocity. If you want the control two axis, you must also use velocity of these axis motion.
Okay, good. And so,
And we continue.
yes, Çağrı Hocam, do you have like, I think you have the,
Apply step inputs to each rotor using the thrust measurement module and system identification of the thread of helicopter, and measure thrust level and RPM via the built-in load cell and encoder, and identify damping thrust coefficients and fit to state space model. And the second step, control design and simulation. Use pre-identified SimScape model in MATLAB and Simulink, and tune PID or LQR or any other controller method. Tune control parameters and verify stability in simulation, and check performance. For example, transient response, maximum overshoot value, rise time, setting time, and you can change the this transient response parameter, characteristic of transient response of the system, with changing the control parameters. And the third step is the real-time implementation. Deploy control to hardware and start with small set point change, and test simulations, pitch and travel tracking, and monitor for instabilities. Some work simulation and experimental works is there are some differences, and it is very important for the test setup and performance analysis, and measure rise time, setting time, overshoot, test disturbance rejection, and compare PID, LQR results. And you can use this setup if you want,
Yep.
for example, obtain or design any new control theory, and you can use test your theory, control theory.
Dr. Çağrı, I think you have one experiment set up next to you. So,
Yeah.
is it possible you can show us a short demonstration about how we, for example, deploy our code controller and what are the blocks we have, maybe?
Okay, and
So you will need to present your screen from the present
Yeah.
screen button, share screen button.
do you see the screen?
Not yet.
Yep, I think now, as soon as you say run, it will come.
I think it's done.
Okay, so
Can you see my screen?
not yet, unfortunately. So maybe let me
You can share directly the kits with your camera as well.
yeah, maybe you can run it, and I will be showing the code from my own computer, so you can. Now it is maybe. So,
Normally, I see the sharing my screen.
yeah.
You cannot see actually.
Okay. I'll do the screen sharing of the MATLAB code maybe. So meanwhile, if you can start running the hardware. Apologies. Okay, here we are. So so this is our one example code that we have. It is
Actually, we cannot see as well. We cannot see.
let's see still. Oh, just a second, maybe from here as well. Let me share it. Additionally. Now, can you see it? Hopefully.
Yeah.
Yep. Okay. So I will introduce the codes. So this one is for like a simple LQR controller code. It is only controlling the pitch axis. So we have the pitch controls here just as a startup example. And so we have here input blocks. This is for the encoder inputs, and we receive both like the yaw and pitch path elevation and travel, in other words. And there's also the output to the both electrical motors through the PWM blocks. And as you notice, this is having only some simple inputs of the matrices, and we have here like some code that is like going through these inputs and outputs. Actually, I have a better documented version. So let me open the better documented version, not this one. Sorry. Oops.
Here it is. Yeah.
The better documented version is somewhere here. I can find it. Sorry. Yeah, here we are.
Yeah.
So we have the parameters at the beginning for sure, and the inertias and all the constraints, and then again more parameters. And also the kind of a constant value for PWM signal as start. And then we define here our A, B, C, and D matrices as Dr. Arijan described. And once we complete these descriptions, we just do a small augmented matrices instead of like just directly using the initial values that way. And the important part is where we are creating the stem state feedback controller, which is just over here. So LQR input, and then A, B, and Q and U matrices as defined here. So this is the one implementation of the LQR matrix. And additionally, we also have simple PID related controllers to do like yaw and to make kind of a set point controls. And this is much more simpler, but these are all like provided with the experiment kit as well. So let us proceed with the presentation part, and I think for the demonstration we will need to share some link to the audience, and we will try to do demonstrations like through offline activities. So we have like a small comparison between the methods that we discussed. So if you also notice that we are comparing the LQR, and also there's the LQG version, which includes an additional Kalman filter to get rid of the noise in the system, which is inherently available. Although for our setup it is much less, but it is always there. So the main takeaway here is that the PID is simple and widely known, and it can be used like with a workaround solution maybe. But the LQR and LQG are they are built for MIMO systems for sure, and they are the most optimal controllers for like these systems. And then, so I also would like to discuss a little bit about the experiment kit itself. So yeah, it is like our trade-off Copter experiment kit. The experiment kit consists of 3 units and 4 parts in reality. I will explain all units one by one. And it is a really compact, lab-ready product. It can be used for teaching simple PID experiments as well, that you can lock the some axes and do some operations. And additionally, we provide software libraries for I/O interaction, so the users don't need to deal with the low-level driver topics or issues. And this is the base unit of the kit. So everything is like connected to this base unit. It is USB powered or separate adapter power if the USB Type-C is not sufficient or not working on the computer. So we have a Raspberry Pico microcontroller inside on this board. And there is also an optional bay here. There is a small like a latch over there. So in that optional bay, another controller like Raspberry Pi or similar controllers can be used to to try some other maybe AI related algorithms. And we have input and outputs for DC motor controllers and some SPI I2C communication buses, as well as a small OLED screen for presenting live data. Next, we place the Copter tower, which is normally here. On the slide, there's an animation problem, but the Copter tower is connected to that part. And it is like it has a built-in slip ring for unlimited yaw motion and has counterweight. So let me try to show over here maybe. So we have the counterweight, and the propeller cages can be unplugged and replugged, so people can 3D print their own propeller mechanisms. And this one is also an important part of the kit. It is called Thrust Measurement Module, and this is used for the system identification part of an experiment. So it has sensors for measuring the current and voltage levels applied to the DC motor, and also the encoder to measure its speed. But we also have a load cell, which is just over here. So the load cell is to measure the force output, which is a thrust in that sense. So we relate the input and output characteristics in that way. Additionally, we have some spare parts over there. Here, maybe it can be seen. So close to the load cell. So it can be used to measure the signals with an external equipment as well. And finally, we have the I/O test unit. It is a simple I/O card that has some GPIO signals. And we also have the IMU sensor that can be replaced over here and then taken back to the propeller main tower as well. It gives like access to external ports for measurements. So this port is used for preliminary or preparation tasks of the students. So they get used to the signals, they get used to the MATLAB Simulink environment, or Python or C++, whichever is used. And then afterwards, they will start to system identification using the trust measurement module, and eventually they go into the Copter tower module to do the full experiment. So we will also discuss a little bit about the same where these LQR principles or MIMO system principles are applied in the physical world, in the real world, not only conceptual or educational purposes. So we definitely, the MIMO control is used with UAVs and the helicopters, like the Chinook helicopter that we discussed, and also the robotics, which initially I described. The multi-axis robot arm coordination is a MIMO control problem, or it is already solved problem, but these strategies are used. And alternatively, in the automotive, the braking and steering systems are also MIMO, because there are multiple wheels and multiple like brake calipers, etc. So each has some effect on the performance of the braking or on the steering angles, so on and so forth. And finally, for chemical processes, the temperature and pressure in chemical reactors, they are kind of coupled to each other. So when the temperature rises, the pressure goes up, or vice versa, depending on the type of the process. So again, MIMO control, sometimes LQR or sometimes model predictive, different type or different MIMO controller setups or strategies are utilized in the chemical industry or any process control that's having such a relationship. So this concludes the slideshow presentation task part of our today's webinar. I think we will be sharing a link for further demonstration, one-to-one demonstrations, so that we will be running the experiment kit and doing some like more hands-on experiments with the prospect people who are really interested to use the system. If there are any questions, now we can take the questions. If there isn't any question for now, I think so. The production team says, okay, use the 1 or 2 more minutes to wait for the latency. So,
Dr. Charlie, could you show the kit for us?
Yeah,
We
the camera, you can rotate the.
Yeah.
Yep.
Now it looks better.
Actually, we have some videos on YouTube as well. Maybe we should have started with showing the videos initially, but again, for the people who would like to see the each part, like the close manner, so the videos might be also a good point to check. And okay then. So if there isn't any further question, or if there will be any question, we will be answering them offline as well. I would like to thank you, Dr. Fethi and Dr. Chare, for joining me in today's webinar, and hope that we will be meeting in the future in a follow-up webinar on the kit, maybe some new algorithms that are implemented. Okay, thank you.
Thank you. Bye-bye.
Thank you.